we just jump into our last two presentations, which are also related a bit about the testing, but let's say alternative methods. So the first presentation will be given by Ennio, and you can already start your screen. Ennio is the deputy head of business development at ESRF, and his research career he worked on the development on electrochemical nanobiosensors, composites, optoelectronic devices, in particular for the characterization for synchrotron light. At ESRF, he's coordinating the participation of ESRF in various collaborative initiatives with industry, and in particular on energy storage application, additive manufacturing methods, and nanoscience. And since 2020, Ennio is the director of the platform Advanced Characterization of the Technological Research Institute NanoElect. And furthermore, since 2021, he is collaborating with the initiative Ratnitz, which we heard already, where he is in charge of the industrial program. And he is now giving a presentation about alternative solutions for heavy ion testing, which we know heavy ion testing is quite expensive. And we are looking forward for your talk.
Thank you very much, Ian. I want to say that you're not at all off schedule, because considering how packed up is the program, I'm impressed by your chairing that we're there. So I would try to stick with the quality of my predecessor. So I'm Ennio Capria. I'm today talking from the ESRF, which is the European Synchrotron. In a synchrotron, normally we generate X-rays, so someone can start thinking, why X-rays? We're talking about space. I hope that this is going to be clear at the end of my presentation, in particular because here we talk very much about how to overcome one of the biggest barriers that are today identified in the world of irradiation testing, in particular for space, which is the availability of heavy ion for single event effect testing, and in particular the availability of high energy heavy ion to really have a much higher depth penetration, like it's normally for the last generation of components and packaging. So going up in your presentation, basically everything started when I started asking around me and my colleagues doing heavy ions, what's your wish list? What would you like if you could have a magic stick to change? And basically I identified three main characteristics. The first one was, of course, having larger capacity, because heavy ions today are the absolute tool for qualification. The second was the possibility to have focused beam, not always, but in some cases having focused beam can allow you to interrogate some specific area of your component and having a much easier and precise debugging in particular phase of R&D and not of qualification. And moreover, the possibility to have high energy heavy ions for two simple reasons. The first is that in some cases you can have a simplified sample preparation. Basically, you don't have to decapsulate your components if they are flip chip, so or they are even if you have some materials that are complex, and in some cases the decapsulation is extremely difficult and can bring the possibility of not completing at all your testing, as was said by my colleagues before me. But also because in some case the appearance of complex packaging is really making the testing without high energy impossible, because you don't have enough energy to penetrate at the stage and the place where your active area is. Here is very much a picture just to show what we are talking about. And as you can see, the trend in this year of going up with 3D integration is much higher, because the miniaturization, of course, is increasing. We want more components in the single area, and going 3D is one of the options. And of course, when we go high energy, the ions that are available doesn't have ranges that are high enough. to go in. So yeah, I show, for example, a typical ion xenon 2G can go down to 156 microns, which for a sample, a standard electronic circuit in 2D with a face up, it's okay. If you start to be face down, and even in multi-stack, this is not viable. So one of the idea to overcome those wish list, or in order to enable this wish list, was okay, why we don't stick, we start thinking about other ways to emulate heavy ions, and this is how photons came into the equation. Of course, photons deposit a charge and energy using photoelectric absorption, which is not like the Columbian interaction, but at the end, with photons, you can deposit the critical charge in the active area. So at the end, you can effectively stimulate and induce a single event. So definitely, photons can be a way to emulate heavy ions. And today, focused laser has been an alternative that tends to be generalized. So you can see more and more equipment in the lab and actors in the lab that are taking a sample, are taking some laser in their on a bench top and doing this experiment. But of course, if you think about laser, they can only solve two of those wishes. The higher energy will not be possible with lasers because, of course, they cannot penetrate enough. And that's how the idea of X-rays came into the equation. Okay, I just take a pin to say X-rays here. So the idea of having simplified sample preparation and complex packaging. For example, just to give you an idea, why I cannot pass the slide anymore. Okay. A 15 keV photon X-rays can produce 3,000 pairs. So you can actually produce a charge of 1 e to the 3 electrons in your active area. And this, if you compare with the charges that normally are generated by heavy ions, can bring you to the possibility to have effectively, if you have an intensity high enough of X-rays, this could be a possibility. Now, someone can tell me you are discovering the hot water because, I mean, X-rays has been there for ages. So why only now you are going and start talking about this? It's because, unfortunately, when we are going to deposit the dose, so you are inducing some TID, X-rays in the lab are enough. But when we want to induce SET, we need an intensity of X-rays which is not achievable in a laboratory. And that's where the synchrotron X-rays, which are facilities that are large as a football stadium and are dedicated to generate high brilliant X-rays, come into being. In the facilities like the ESRF, we can generate very high energy X-rays with very high intensity. In particular, we can generate some pulses and focused beam. So in this case, this is something that is pretty unique, that you need to find this facility and is not available with the X-rays that you have in the lab. In the lab, you will not have intensity high enough to generate this single event. You can only do TID. So for single event, you have to go to synchrotron. For example, on the beamline ID09 at the SRF, we can have a possibility to generate pulsed X-rays, which has a commuting time, a length of 150 picosecond on a diameter of 35 microns, and we can generate 4 e to the 9 photon per pulse. So these 3,000 electrons that you have seen before, you can multiply for the number of pulses. And so in this case, you can arrive to deposit a pulse of 9.6 microjoule on your device. So for people that are familiar with this unit, and in particular using lasers, this is the amount of energy that can be enough to generate your single event. Of course, we can also reduce the diameter, focusing a bit, and this focusing activity is going more and more. The beams are monochromatic almost, as you can see. This is the shape. So we have to be very careful about the energy, because if we are not in the right energy that is enabled on the beamline, this is going to fail. So three important values that are important that are there are the pulse energy, which is normally correlated with the LET, and the photon energy, which is normally basically the wavelength of your incoming X-ray beam that is correlated with the penetration depth. So playing with those values, basically, you can emulate a full range of LET that normally you have in your heavy ions, and you can also modulate based on the sample that you have in order to be sure to reach the active area. Here you can see on some experiment that's been done by some colleagues in the US, in the group of in Aerospace Corporation, in the group of La Lumondière, who were the pioneers on this methodology, how the shape of a transient of an X-ray SCT generated is very similar between X-ray and heavy ions, and in this case also lasers. And still the group of Cardoza in silicon, they also made a first evaluation and a first demonstration of how we can emulate a series of LET with the appropriate energy of the pulse. And here we can see, for example, choosing a different value of energy of your incoming photon. How you can consider here we simulated what's happening with a die that has 8 dies of silicon, one on top of the other. You can see how the amount of energy basically transmitted across each single layer is decreasing, going layer by layer by layer. The highest is the energy, the highest, of course, is the transmission. So if you have a too low energy, then even X-rays are not good enough. But if you have an energy above 15 keV, normally you can start having a good experiment. Here you can see we consider 10 stack elements. And if you consider what has been done today, what do we know? In what is concerned about logic, we had a good experience of correlation in silicon, analog and digital devices, photodiode, bipolar system, also in silicon germanium, GaN, and gallium arsenide transistor. On power devices, we also have some work that has been published on SiC and on GaN. You're going to receive my presentation, so here you have a comprehensive literature review that I advise you to go through. So this activity of emulation of heavy ions is very important. Why? Because we demonstrate that we can deposit a charge high enough in the active area to generate SCT. In this respect, something that has been also interesting and demonstrated is the pure fault injection. You don't need to come to a synchrotron only to emulate an heavy ion effect, but you can also come to us if you want to inject a fault somewhere for cybersecurity purpose, or even to test how an error is propagated. This idea of testing the error propagation, and so the error mitigation strategy on your device, is gaining importance. So in this case, you're not going to emulate or correlate with any energy, any LET. You just want to generate an error in an area, precise, in a single component, in a portion of a component, and then you can get your elements. So we are still in the phase of validation, of demonstration, of maturation of this technology. If we want to tell in TRL terms, I would say that our instruments are TRL 9, but probably the methodology today is somewhere between 4 and 6, because we are still working with our partners and our colleagues in order to have more proof, to publish more results, to demonstrate the validity of what we do. For fault injection, we are probably above 6, because we don't have this issue of finding the correlation. We just need to arrive there, and we already demonstrate that we can inject the active, the critical charge in the active area. So modeling will be needed, understanding TID as well, because these are still X-rays. So each time that you generate this SE, all the charge you're depositing there can also induce some localized TID effect. And of course, we need more work with partners, and in order to very much demonstrate and make this technique adapted and adopted by the community. If not for qualification, at least for screening and for debugging in the R&D activity. You can access the ESRF via RadNext, so please, if you are interested, don't hesitate to get in touch with me, and in case we can fill together a proposal. And just last but not least, I want to say that at the ESRF in Synchrotrons, our core activity is to do failure analysis with very high resolution, with the tomography, XRD tomography at the next level of possibility. You can see a couple of reference down there. So what will be interesting in working together is that we can definitely test the reliability of your circuit and then go and check what's happening in your circuit. Quickly, a couple of studies. Do you remember this circuit that I show you here? This simulation has been made in real, and this is the results. So as you can see, with 3 different X-ray beam intensity, we could demonstrate how at the different dies positioning, we could have a decrease in the number of error measured. So we can really see how there is a correlation between the absorbed energy and the energy that was transmitted and the number of errors. And then a second interesting experiment is this one on a photodiode, where basically we demonstrated the linearity and how we could correlate the LET measured with the heavy ions with the energy of the pulse that I told you is the equivalent. And this was in the nanojoule. We didn't even have to exploit the whole capability. A takeaway message is there's plenty of synchrotron in the world. So not only the SRF, is the community is there, if there is an interest, we can work together in order to create the capacity. For now, I can tell you that this can be used for fault injection, pre-screening, LET sensitivity characterization. We made it, we demonstrated it, and of course, those can be a problem. And we are very happy to work together to develop this wonderful methodology. And if you're interested, also leverage it on RadNext. Thank you very much.
Thank you very much, Ennio, for this presentation. Very interesting to see how we are ending up in future when it comes to alternative test methods. Specifically, if we're looking to technology trends, so we know system in packages, system on chips, multi-die technologies are getting really, really challenging for classic heavy ion testing. And I think maybe X-rays or pulse X-ray solutions could be come over with that kind of solutions. And yeah, would be interesting to see. Would be interesting to see how the agencies, which are usually quite conservative with alternative test methods, are looking at this trend. But yeah, we will see. I'm really like to thank you once again for this presentation.
Thank you very much.
And I would say we are moving on with the last speaker, and we will tracking the questions to you for sure. As I know, our last presenter has a kind of, let's say, conflict in his schedule. So thank you again, Ennio.